Oh, the exhibitions. What teacher?
So this was where we left off with parametric. Okay, so we had finished this circle one right here, and we were looking at this one right here. Before we even get started, do you know what shape that parametric equation is going to graph?
Ellipse.
Did we do this one?
We started it, but we didn't.
Oh, okay. Or I might have told you guys to do it and then we never went over it.
I think we just ran out of time.
Yeah, the bell rang, I think halfway through. That sounds right. So this one's going to be an ellipse, right? I've got the x cosine, y sine, and the 6 and the 3 are just telling us how spaced out that ellipse is going to go. Okay, so I think you guys might have this all filled in already, but here I go. So to sketch this, I'm going to plug in some values of t. T is going from 0 to 2 pi, so I'm going to start with 0, pi over 2, pi, 3 pi over 2. When I plug in 0, cosine at 0 is 1, so this is 6. Sine at 0 is 0. When I plug in pi over 2, I get 0, 3. Negative 6, 0, 0, negative 3. So here's my ellipse. My x's go left and right, 6 units, and up and down 3 units. And I start here, and it travels in this direction. So I'm going to use arrows to show how my ellipse traveled. Eliminate the parameter and write your equation as a function of x. So we can use sine squared plus cosine squared equals 1 and plug it all in that way, but also we can use our knowledge of an ellipse. This is an ellipse that's centered at 0, 0. So it's x squared plus y squared equals 1. The major axis goes with the x's, left and right 6, so 6 squared is 36. Up and down 3, 3 squared is 9. That's what our final answer should be if we eliminate the parameter using sine squared plus cosine squared. If you did it using trig, you would say that x over 6 equals cosine of t, and y over 3 equals sine of t, and then you would say that sine squared plus cosine squared equals 1, and plug them in. You get the same answer either way. Whether you use your algebra 2 knowledge or your trig knowledge, same thing. Alright, let's find out these derivatives now. So dx dt, this is the left and right motion, the rate at which we're moving left and right. So x is 6 cosine t. When I take that derivative, I get negative 6 sine t. dy dt is my up and down, my rate of up and down motion. My y equals 3 sine t, so this is going to be 3 cosine t. dy dx. Ah, what a crazy x. Let's fix that. So I do my ratio of dy over dx. Simplify that. I get negative 1/2 cotangent of t. And now the second derivative. So I'm doing the derivative d dt of negative 1/2 cotangent of t divided by dx dt. So in my numerator, the derivative is 1/2 cosecant squared t. And in my denominator, I've got my negative 6 sine of t. 1 over sine is cosecant, so I'm going to have 1/2 times negative 1/6, which is negative 1/12. And then I have cosecant cubed t. Pausing for questions, how are we doing?
Why is it dt like the derivative of the, like why is it like that? Do you know what I'm saying?
Why? So that's the formula. If we go all the way back to the beginning over here, the second derivative is d dt dy dx over dx dt. That's the formula to find the second derivative when we're doing differential. So in this problem, I plugged in dy dx from up above and dx dt from up above.
Okay. How do we go from cotangent to cosecant squared?
I took the derivative.
Oh.
So this says take the derivative of this, and that's what I got.
Oh, why don't we square the bottom?
Because the bottom's not squared? I'm confused. This isn't part of it. So here, this was dy dx.
Mm-hmm.
Dx dt is this.
Yeah.
It's not part of the derivative up above.
But doesn't it say dx squared?
That's the result of all of the numbers that I'm evaluating. It's not squared until after I take, so this, here, let me go back up here. This is the result of simplifying this. So in the problem that we're looking at, I plugged in all my stuff, and the result is the second derivative. It's not happening when I plug in at that moment.
Got it.
The dx comes from like the numerator got squared, whatever, all that. Okay, so to find the speed, the formula that we use for speed looks like this.
Wait, what happened to C? Oh, that was C.
So speed is dx dt squared plus dy dt squared. And I'm going to evaluate those at the time pi fourths. So dx dt evaluated when t equals pi fourths is plugging into the dx dt from up here, negative 6 sine t. So negative 6 times the sine of pi fourths, which is negative 3 root 2. Then the second one I'm doing, dy dt, evaluated at time pi fourths. So dy dt was 3 cosine of t, which was pi fourths. Cosine of pi fourths is square root of 2 over 2. So this one ends up being 3 root 2 over 2. And now I plug both of those into my formula for speed. So my speed is the square root negative 3 root 2 squared plus 3 root 2 over 2 squared. So we're going to have, let's see, 9 times 2, this is 18. And this is 9 times 2 over 4. No, this one is
Really?
I guess I could simplify it further, but I'd be allowed to leave that. Okay, so let's find the length of the curve, total distance traveled. Length of the curve formula. So to find the length of the curve, we're doing the integral from time 1 to time 2 of the square root of dx dt squared and dy dt squared, which is really similar to what we just did, except we're not going to be plugging in numbers, we're going to be using the equations. We'll have the sines and the cosines and the t's and the things in it. So we're doing the integral from 0 to 2 pi. And this is the square root of 36 sine squared t and 9 cosine squared t dt. And I do not have a good way to do that by hand. So this would either be a problem where it just says, what's the formula, what's the expression to evaluate the integral, or it would be something that we could do with our calculator. So if we plug this into the calculator, we end up with 29.065. How we feeling? Okay, so we're still looking at the same equations that we were working with in the previous problem. I'm going to copy them down again, and then let's talk about interpreting what this means. It says it wants us to find the highest point, the lowest point, the leftmost point, and the rightmost point. In a parametric equation, that's talking about the maximum and minimum values on our x's and our y's. That's what it's trying to find. And if we are just using what we know from Algebra 2, I know this ellipse, I know the leftmost point is at -6, and the rightmost point is at +6. I know the top is at 0,3 and the bottom is at 0, -3. I know that because I know what the picture looks like. I know the Algebra 2, but let's do the calculus because we won't always know what the picture looks like. We could be asked about something where we have no idea what the picture is. It could be some crazy shape. So to find the highest and the lowest points, I'm asking for the maximum and the minimum of the y values. So these are max and min of y. If I'm looking at the left and rightmost points, those are the maxes and the mins on x. And if I want to know a maximum or a minimum, I want to know the extrema, then I use the derivative. And I'm going to use a first derivative test to see when they equal 0 and test which ones go which way. So first I'll do my x's, okay? So if I know that dx dt was equal to -6 sine of t, now I'm asking, when does that equal 0? So what values does t make sine equal 0? Those t values are at 0, pi, and 2 pi. and I'm going to use the first derivative test to see where it's increasing and decreasing, so I'll know which ones are maximums and which ones are minimums. Okay, when I plug in values that are less than 0, just to the left, those were positive. When I plug in values that are between 0 and pi, that's negative. Pi to 2 pi, positive, and then bigger than 2 pi, negative. I could also use my knowledge of a sine graph. -6 sine, instead of going up, goes down. So it looks like this, right? And so these were positive, these are negative, and then these are positive, and then these are negative. So if I use my knowledge of what a sine curve looks like, I can know that without having to plug things in. It'll save me a little bit of time. So what does that tell me? Well, if this is positive and then negative, this is the location of a max. This is the location of a minimum. And remember, we're only looking on our interval from 0 to 2 pi. So now let's write out what I found. We have a horizontal maximum at time 0 when the point is 6, 0. I should say at, not when. I have a horizontal, oh no, minimum at time equals pi, -6, 0. I kind of like the algebra 2 way better, right? But we won't always be able to use that, right? We might have things we don't know what they look like.
Wait, so how did we know that, like without looking at the picture, how did we know that it was 6, 0 and -6, 0?
Oh, I would have had to plug into the original equation. So I would have had to plug in over here and say at time 0, what do these equal? Which we figured out up here, right? At time 0, I figured out that it was at 6, 0. And then at time pi, I was at -6, 0. So I plug in t, find x and y to the original equation. Okay, so now repeat the process for dy dt. So dy dt equals, that one is 3 cosine t, and that equals 0 at times pi over 2 and 3 pi over 2. We do our first derivative test. So here's pi over 2, here's 3 pi over 2. Values to the left of that are positive, negative, positive. So we say that we have a vertical maximum at t equals pi over 2, 0, 3. And we have a vertical minimum at t equals 3 pi over 2, and that one's located at 0, -3. Okay, so let's talk about tangents to the curve. All the vertical and horizontal tangents to the curve, vertical tangents to the curve happen when the slope of the line is undefined. So dy dx equals the slope of the tangent to the curve. If dy dx equals 0, then we have a horizontal tangent. If dy dx is undefined, then we have a vertical tangent. And we knew from up above dy dx was already figured out. So I want to show you two different things. Cotangent is nice and all, but since I'm looking for when the numerator or the denominator equals 0, it's actually kind of easier to look at the cosine over sine version of it because it helps me to wrap my head around it. So this is -1/2 cosine over sine. Okay, so horizontal, when the numerator equals 0, when does cosine equal 0? That happens at pi over 2 and 3 pi over 2. So cosine of t equals 0 when t equals pi over 2 and 3 pi over 2. We figured that out up above, right? So that happens when x equals 6 and x equals -6. These are tangent lines. They have to be written as lines. And then the vertical tangent, when it's undefined, happens when sine of t equals 0. And we said that happened at 0 and pi. And so that was when y equals 3 and y equals -3. And again, if we go back to what we know about algebra 2 trig, we can see those are the places when the tangent line is going to be vertical or horizontal. We know that just by looking at the picture. How we feeling? Okay, I've been talking too much. Now it's your turn. Eliminate the parameter for each of these parametric equations. Here are the things that you need to know to eliminate parameters. You need to know that sine squared plus cosine squared equals 1. You also need to know a double angle formula for cosine. See this one? So cosine of 2t, do you remember the double angle formulas? There are 3 choices. It's either cosine squared minus sine squared, or 2 cosine squared minus 1, or 1 minus 2 sine squared. That's the double angle formula. So if you have those pieces of information, I think you can eliminate the parameter for all of these. So. All right, I'm going to stop the recording and then we'll check in on these in 4 minutes. And Anthony, if you want to move to another table so you can talk to people, you can. You don't have to be all alone.